Ladies and gentlemen, we're going to introduce Chapter 13, Nuclear Magnetic Resonance. Those words are loaded. Can you remind me what is in the nucleus of an atom? Protons and neutrons. We're going to focus on just the proton for one simple reason. You don't need physics for this course, but I'm going to give you some basic physics, just facts. Just accept them. They're true. They've been proven hundreds of years ago. Okay? If a proton is rotating, which all protons are, it's something they do. They have spin. You've heard about it, right? So a rotating proton, if you have your right hand and you curve your fingers, pretend your fingers are an arrow for the direction of the rotation. So in this case, I'm looking at it. If you look there, that is counterclockwise. Now, by using your right hand, you've just predicted the direction of the magnetic field. It's upwards, caused by that rotating proton, the counterclockwise one. Yes, rotating charges cause magnetic fields. It's a fact. You want a bigger magnetic field? Make the charge go in a bigger circle, like actually have the thing travel in a circle. And it works not just for protons, it's for any charge, electrons too. So how do you make a big electromagnet? You've heard of those, right? Easy. You get a copper wire and you wrap it around in a circle hundreds and hundreds of times, and then you force electricity through it. Just plug it in the wall, okay? And then, yeah. And you have created an electromagnet. Now, for the purpose of NMR, that electromagnet's actually a part of this too. So it's about the magnets in the nucleus interacting with an electromagnet that you've made. And you guys know, back when you were a little toddler, you learned about magnets a little bit, right? You got those bar magnets, remember those, north-south? You put them close to each other and they're lined up, they snap together. Well, you guys are chemists now, right? Isn't that a force of attraction? A stabilization, if you will? Now, if you flipped those magnets, you couldn't get them anywhere near each other. They kept pushing apart from each other, right? There's a repulsion. Okay, so if they're not lined up, that's destabilizing. And you guys always think in potential energy, right? Stabilizing, that's when the magnets were lined up, goes down. Destabilizing, if your magnets are misaligned, they don't match, their poles are opposite. Okay? So let's go back to the nucleus. Forget about the electromagnet for now. We're just talking about protons in the nucleus. They're rotating this way, creating magnetic fields like this. That's half of them. And the other half are rotating this way, which is clockwise. And what direction is my thumb? It's down. And there's one is not favored over the other. There's a 50-50 mixture of all the protons in your nuclei rotating clockwise and counterclockwise. That should make sense, right? All right. So inside that nucleus, there's a magnet. Now, in certain nuclei, those magnets, there's as many magnets one way as the other, and they kind of cancel each other. So you need an unbalanced nucleus. And I'm not going to go into the physics behind why certain nuclei work for NMR and certain nuclei don't do anything. They're like invisible. But hydrogen atoms are perfect because the main isotope has got one proton, right? And that's it. And it creates a magnetic field all the time. And we know every organic molecule has H bonded to C. This is great. So if we have a calling card for those hydrogens, we can actually see them. And we do. The environment the hydrogen's in the molecule tells us how strong its magnet is. Okay? So we have spinning charges in the nucleus. Spinning charges in the nucleus. That's protons, right? What do spinning charges cause again? magnetic fields. These will interact with an external electromagnet. Okay? Here's the deal. My spinning charge, here it is, and this one is rotating. Let's try it this way. Here. Okay, and that's this one, and that causes a magnetic field upward. HP. Okay? I call that H is magnetic field. That's a physics thing. We got to get used to it. That's confusing as all get up, because we're going to talk about hydrogen atoms a lot. But when I write H with a sub thing P, that means magnetic field. H is magnetic field, and HP is magnetic field of a proton. Okay, so we got our other proton, right? If it's rotating the other way, that's going to cause HP like this, right? We good? And if you're taking physics, they're going to tell you that, and that's called the right hand rule. You have to use your right hand. And they won't tell you because they don't think it's important, but it is important. If you're talking about electrons, use the left hand. Same idea. What is the magnetic field of an electron rotating clockwise? Well, that's clockwise. It's up. It's kind of the opposite of the protons. You'd probably predict that anyway, right? Because you just change your hands, it's going to be opposite. There's a whole field called electron spinning spectroscopy, electron spinning magnet, NMR. Anyway, there's a lot of stuff about it. We're not going to do it. We're only talking about NMR, nuclear. Okay, now my electromagnet's going to be blue. And I am not blue. And it's big. That's why I drew it big like that. And I'm going to call this H naught. That's the magnetic field of your electromagnet. Magnetic field of electromagnet. So you turn that thing on, and you started with two protons. One was doing this magnetic field, and the other was this. And now they're not going to be the same energy. One is going to interact in a stabilizing way with the electromagnet, and the other is going to be destabilized by the electromagnet. And guys, if they're lined up, they stabilize. It's very simple. And if they're not lined up, they destabilize. So your new energies are here and here. One went down the same amount, the other went up. And the one that's lined up is now more stable. And sadly, my pictures are starting to roll into each other. Let's keep this separate here. We got this guy right here. These all go in one picture. So this, when it interacted with these two guys that started with the same energy, this is a potential energy diagram, by the way. PE. Now they're not the same energy. And this is when you start getting very excited. Because now you can differentiate between the two states and use some kind of spectroscopy to see. What you need to do now is turn on some kind of energy source that will allow you to excite this spinning proton, that one, right? Am I sharing the screen at all? Yeah, I'm sharing. So, little picture. Yep. I want to cause that guy to absorb energy so that his spin goes to the other direction. It's kind of like you got this guy here. You want to get it to spin, change direction. You kind of hit it, right? I hit it with my hand. It was going this way, and I banged it that way, and it went this way now. Well, you just have to find the right frequency of energy to bang it with. And it's unique for each type of hydrogen in the molecule. The gap in energy there is unique. How big this gap is unique to the type of hydrogen in the molecule. That means every hydrogen has its own little frequency that you can tickle. You got to turn on the right frequency. And as soon as you have the right frequency, it starts absorbing it, the energy, and it goes from this state to this state. The important thing is to absorb that energy. So you have that energy going into the machine, and you have a detector on the outside, and it's not coming out. Why? Because it got absorbed by that hydrogen that has that right frequency. So we can tell that hydrogen's there just by using a detector. Okay, so NMR's got a lot of cool stuff in it. The amount of energy to get this to go from here to here is very low form of energy, the lowest form of electromagnetic radiation possible. What do you call that? The lowest energy form. Don't tell me gamma rays. You're on the opposite end of the spectrum. That's the most dangerous form. What's the other end of the spectrum? Where the wavelengths can be up to a mile long. I'll start at the top, and you better give me the bottom before I have to do the whole list. You got gamma and alpha and ultraviolet and visible, and guys, I'm running out. Red, go lower, microwave. No, X was way up there. I missed it. I'm sorry. It was below the alpha. Guys, we're living in a different energy, different time now than when I was young, because everybody would know back in the day that radio waves were the lowest energy because we listened to radio. You guys don't do radio anymore. You don't think about radio at all. It's okay. There's just radio on the internet. So radio waves have the right frequency. So your machine has a lot of stuff in it. It has this huge electromagnet. For a good machine, it's a lot bigger than me, right? Now the machine I used, we had to go up a staircase, and the electromagnet was about that wide and about 4 feet tall. And that was a pretty good machine, but they have better machines. They're multi-million-dollar machines. And it's worth every penny. Because when you get to that machine, you can start analyzing proteins, which have thousands of hydrogen. Anyway, so if you have a bigger electromagnet, you can spread this gap out bigger. It gets to be a bigger gap. If you double the strength of this, you double the gap here. It's linear, people. And you get better resolution because you can tell the difference between very similar hydrogens better if there's bigger gaps, right? But if they're real close in energy, you say, is that a new peak or is that part of an old peak? They're overlapping, but with a great machine, it separates them all out. So what's the take-home message now? We got to get to that last word before I let you go. We didn't do the R word. You guys think you know what the R word means. I know you do. We got to figure out what about your old definition of the R word fits with this new concept of the same R word, even though they're very different. What was your old concept of the R word? If you had to just define it based on your knowledge from past, what do you mean? What do you mean by resonance? Okay. Electrons moving back and forth in the same molecule. I like the only thing about that definition that works here as well is the back and forth. So forget about the E word. Forget about moving. Okay. We're resonating. It's going between different states, right? Two resonance forms. You're going back and forth. Here, you're going back and forth when you turn on the radio transmitter that you need to, with the right frequency, it bumps that proton that used to be spinning that way and hit it with the right energy to spin it the other way. Now it's excited. It went up here. And it doesn't want to stay up there, does it? If you're in an excited state, you stay there forever? No. You relax back down. Oh, and then you're going to absorb that energy again because you left your radio on. Oh, back up, and then it's going to come back down. And then it gets excited again to the upper state and comes back down. What's that called? That's the resonance. You're resonating between two spin states. That's a good way to remember. Just keep doing that. What resonance you talking about? He's doing that with his hand. I don't know what he means. Okay. Good introduction.